Hello everyone, my name is Mohammed Al Amin and I am application engineer at Altair. Today I will be talking about electric drive concept design using Altair FluxMotor. Here's the agenda for today. So I will start by introduction of electric drive, and then I will move to introduction to Altair FluxMotor, followed by a case study and a demo for the tool. So the transportation OEMs need sustainable technologies to meet customer demands and government regulation, especially with respect to the global warming. So they are looking for safer, lighter, greener, and smarter vehicles. And that's why today we see the push toward e-mobility, which represents the concept of using an electric powertrain. An electric powertrain typically consists of these main components, which are the traction motor, generator, the battery, the power electronics, which includes the inverter but is not limited to it, and the system modeling and control to control the power transfer between all these components. The design of high-end e-motor for electric vehicles is not limited only to the electromagnetic part, but also include other disciplines such as structural, CFD, NVH, and a system simulation. So we need to come with a better workflow to include all this part together to make sure the design meets the requirement. So I will leave you with this short video which explains about this process. So in short, we can break the design into three stages. The first one is the concept design, where we explore a large set of topologies and select the best one which meet the requirement and come with an initial design. And after that, we move into the detailed design, which typically involve multiple physics, including the electromagnetic, the CFD, the structural, and the NVH. And it's typically the case that we can put all of this under DOE and optimization studies and run them together to come with the optimum and the best design. After that, we move to the system integration part, where we include the battery and the inverter as well and make sure all of this work together to meet the requirement. In this webinar, I will have specific focus about the concept design, which is the first stage, in which we have our tool is called Altair FluxMotor. So next, I want to give you a general overview about Altair FluxMotor and its capability. So Altair FluxMotor is a dedicated standalone multiphysics environment to accelerate the design of e-motor concept. It allows fast evaluation of techno-economic performance, which include rapid concept exploration, product feasibility check, support user to make a documented decision quickly. It's accessible to broad range of users, which could include and not limited to motor designers, motor integrator, teachers, students, and so on. And that's because it's really has intuitive interface and workflow, and it's really easy to use. With no simulation knowledge needed, it has customizable template which are completely parameterized, a user-oriented winding tool, a predefined test with automated reporting, and you can literally build, machine, test it, and produce the report in a matter of minutes, not hours. It's really fast and accurate. It's used mixed finite element solver in the background, and also some analytical calculation with embedded modeling knowledge about e-motors, and also optimization process in the background. It has effective machine part management. There are standard libraries provided with the tool, cover a large set of motor topology, including the slots, magnet, and bars. Again, all of these are parameterized, and even if you don't find specific shape you want, you can actually customize and create your own parts in Flux Motor. And it also includes efficient project management. You can access quickly your past studies. You can categorize them into different catalogs. You can have quick performance comparison and ranking between the different designs. It also allows you to, after you come with your finalized e-motor concept design or initial design, it allows you for further connection for advanced studies. So Flux Motor is mainly for the design of radial flux machine, which cover more than 90% of the motors in the market today. So it can do synchronous machine with permanent magnet with inner or outer rotor. And it can also model induction machine with square cage with inner or outer rotor as well. And with the possibility also to add skewing to the slot, magnet, and bars. And there's more machines types to come in the future. The next release of Flux Motor, which is in November, December this year, will include the synchronous reluctance machine, for example. So what are the tests that are available in Flux Motor to evaluate electric motor design? So as I said before, in Flux Motor, there's no need to put any effort into the post-processing, and the results are automatically illustrated after the test is finished. So from electromagnetic point of view, we can run an open circuit test and look at the back EMF test and the cogging torque. And we can characterize our motors that give us a different maps in the ID, IQ range. We can also run a datasheet test to find the corner point or the base point of the motor, giving limit on the current and the voltage available. We can also run and see the performance of the motor at specific working point. And we can also run our motor across the entire speed range and see the efficiency map and its performance. On top of that, we can also evaluate at duty cycle defined by speed and torque against time and look at things like what are the average losses during the duty cycle and what are the average efficiency. During the design of electric motors, we should make sure that the temperature inside the motor doesn't exceed a specific limit. Otherwise, we are risk damaging the motor. And for that reason, we have to make sure that we are designing an efficient cooling method to extract the heat out of the motor. So Flux Motor allow you to design different housing with fins and or cooling circuit and apply different external and internal cooling. And then it allow you to run a steady state thermal test to look at the temperature distribution along the different parts of the motor. In this case, the heat source will be provided as a set of losses in the stator, rotor, and the winding of the motor. It also allows you to characterize the thermal network of the motor provided by different thermal resistance between the different components inside the motor. And it also allows you to get the losses directly from one of the EMF tests already performed in Flux Motor and use it as a heat source in the thermal test, or do it in iterative process where you actually run the EMF to get the losses, provide it as a heat source to the thermal part, and then run the thermal part to get the temperature and update the material properties and run the EMAG again, and then follow this process until it reaches convergence. Also in the next version of Flux Motor, the transient thermal will be available. Flux Motor also allow NVH prediction in the early concept design phase. Although these are just preliminary results and it's not as accurate as the complete FEA solution, but it can give you a great insight into any future problem or issue. There are two different tests you can run. The first one is the single working point test, where you can get results such as the model analysis, the radiated sound power, and the electromagnetic forces on T's. You can also run the test across the speed range and look at the radiated sound power versus speed and frequency range, or what's called the waterfall diagram. Or you can look at the order cut analysis and see which order is contributing the most to the noise. Or you can look at the overall weighted radiated sound power versus speed. As we have seen in the introduction part, once you are finished with the first stage, which is the concept design, you want to move to the second stage, which is the detailed design. So Flux Motor allows a connection for advanced studies, which include Flux, which is our full-fledged electromagnetic FEA tools. So in Flux, you can do all type of advanced electromagnetic analysis, which is not possible in Flux, such as eccentricity analysis, demagnetization, short circuit, compute electromagnetic forces, and export it for other mechanical tools. So in this case, the model will be fully parameterized in Flux. All the physical properties defined in Flux Motor will be embedded, and the model is really ready to be solved and post-processed in Flux without anything defined from the user. So in a way, you can think of Flux Motor also as a preprocessor for Flux. It also allows the connection with hybrid study, with our design of experiment and optimization tools. And in there, you can run directly the optimization using Flux Motor as a solver. And indeed, you can actually access all the runs in Flux Motor if you want to look further at the result. You can also optimize the motor not only in a single operating point, but optimizing considering the full duty cycle, which make more sense on electric vehicle application. Flux Motor also allow you to export an FMU, which stands to Functional Mockup Unit. It's a format which is accepted with many system simulation tools such as Activate or other environment, and it allows you to have a reduced order model instead of running a cost simulation with high fidelity, which takes a lot of time. So now we know about Flux Motor and its capabilities. Let's look at one case study in how Flux Motor can be used. In this case study, we want to design a new EV motor with the goal to optimize the efficiency of the motor over the entire duty cycle. In this case, the duty cycle is based on WLTP, which shown to the right here, defining by different speed and torque requirement at each specific time during the cycle. The design variables here are to modify the rotor shape only, with the stator shape being fixed. And of course, we need to keep the requirement needed from the motor as a constraint on the study, which is the base torque should be greater than 180 Newton meter and the base speed greater than 5,000 RPM. So here's the workflow that we can follow to optimize the motor efficiency over the entire duty cycle. So starting from the specification we come with the initial design. For the initial design, we evaluate the efficiency and use that as our baseline. And then we run several iterations for DOE and optimization over the initial design, or starting from the initial design to come with our optimum solution, and then evaluate the optimum solution over the duty cycle and then compare it with the baseline. So here is the first step where we start from the specification and we come with the initial design, which you can see to the right here, with the stator outer diameter of 180 millimeter. The length is 25 millimeter. Number of stator slot is 54, and the number of poles is 6. And then we have this initial design modeled in Flux Motor, so we can put all of this through the design tab here by following a step-by-step process, start from templates, and the model will be automatically parameterized. After we put our initial design, we can run the performance mapping test to come with the efficiency map, and then we can evaluate the average efficiency over the duty cycle, which in this case is around 71%. And then from the initial rotor shape, we have around 22 design variables in the rotor part, which we can use in the DOE and optimization studies. The performance to be maximized again is the efficiency over the duty cycle, and we should respect the phase current not to exceed 280 amp, and this limitation, as we see coming from the specification, and it's really limited from the inverter side. So the DOE will help evaluate the different design variables to understand which one has a dominant effect on the objective and the constraint. So using this result, 10 design variables over 22 can be screened out from the optimization study. In the optimization studies, run around 50 runs with 5 multi-execution, and all of this can be done within 1 hour. And the optimized duty cycle machine efficiency increased by almost 3% from 71% to 74%. And also on top of that, the optimized design save around 32% on magnet mass. So this case studies kind of show the power of flux motor, where you can actually explore a lot of design correctly in a short amount of time. Now I will show you how flux motor actually works through a demo. So in this demo, we'll be designing a PM motor for electric powertrain to meet the specification on the table on the left here. So from this specification, we typically go through analytical calculation to estimate the main dimension of the motor. In this case, I have a stack length of 150 millimeter and the stator OD 198 millimeter, and then we have to decide on a basic selection, which includes the rotor topology, the slot pole combination, and what is the material to be used in the design. So starting from this table here, we will start putting the data into Flux Motor. Well, I will start the demo by opening the most recent version of Flux Motor, which is 2020.1. So the main interface of the Flux Motor allow you to start building a new motor. You can see the different type available here. It also shows you the most recent op-amp motor in the bottom here. In the left side, you have the help and the resources down there, and then you have different user preferences to use from, and then you have the unit, which allow you to change the unit which you will have the inputs and the outputs inside Flux. For example, you can have the dimension put in inches instead of millimeters. Then you have the script factory. This is something which is still in beta mode, but basically the idea is to allow you to use scripting to design your motors instead of using the GUI. The material manager has all the reference materials available inside Flux Motor. It also allows you to create your own materials. The part library, you can go and explore the different standard parts available and also modify them if needed, and building your own parts. The motor catalog is an environment where you can save your different designs and put them in different catalogs and compare them together. So in this case, I will start with the motor catalog. So the motor catalog include all the different design. There are some reference catalog included as an example down here, and the user catalog are in here. So if you select specific catalog and specific motor, you can see general data about the motor directly from here, including its dimension and main information. And if the tests are already solved in this design, you can also look at the performance. More, you can actually compare two different motor design together. So what you need to do, you need to select the specific motor design that you want and add it to the comparator. You can add as many as you want, and then basically click on compare, and this will put all the design you added side by side, so you can compare either the dimension or the performance of them together. And you can also do ranking of the performance if needed. So in this case, I already put the information about the design I specified earlier, and I will go ahead and open that design and guide you through the different inputs we need to build the motor in Flux Motor and the different tests that we can run in the motor. So I put this under this catalog, and here's the motor I'm going to use for demo. So I can just double click on this motor, and it's going to open a new environment which called the motor factory. And this is where we can do the design, test, and export of our design. So in this environment, the first thing you will notice that we have three tabs here, starting from the design, where we put the dimension and the information about the motor. The next part is the test, where current the different predefined test in Flux Motor, and the third part is export. So starting from the design, the workflow is always to go from the left to the right. So again, as I said, all the input are already defined here, and what I'm going to show is basically go through this different input to understand what it means. So the first things about how this GUI is defined, you will always see that the input is in the right side, then you have the view in the middle, and then you have the output in the left. And using the output, you can actually go through different part of the view. So the first thing we are going to do is to put the main dimension of the motor. There are different inputs mode you can select from. In this case, we are selecting the inner diameter to be the resulting dimension. So we start by putting the OD of the stator, the length of the motor, the number of slots in the stator, the air gap length, the OD and the ID of the rotor, and the number of poles. And all of these are actually computed analytically during the initial design stage. Once you put that, you can apply the input. So the next part is to go to the housing, and this part is needed specifically if you are interested on the thermal result. Otherwise, if you're just looking at the electromagnetic result, you can ignore the part about the housing and the shaft as well. So we start by first selecting our frame type. So you can select circular or square frame, and you can put the dimension of the thickness and the extension of the frame in the connection side, which shown here as CS, or the opposite connection side, OCS. Then you can add fins if you have any in the motor. We don't have one in this design. And then you move to the cooling circuit. So this motor will be liquid cooled due to the high power density in this motor. And in this case, there are different types of the cooling circuit, the zigzag type and the solenoid type. In this case, we will select the solenoid type. This can have a circular cross-section or a rectangular cross-section. We'll go with the circular cross-section, and we have around 12 turns around the water jacket, and you can put the dimension of this of the cross-section, which is 5 for the height and 5 for the width as well. So once we are done with the housing, we'll move to the shaft, and we can decide to have a shaft here. As I said, it's important for the thermal point of view because it can extract some heat of the motor. So this information we have about the shaft, and we can also include the bearing here as well. So in this case, I'm actually completely using the default dimension. I just adjusted the extension for the shaft to be the same as the housing. Next part is to move to define the rotor shape and specifically the magnet. So as I said, Flux Motor come with a complete set of standard libraries to choose from. For example, you have libraries here to cover the ring magnets for an SPM type of motors, or V-shaped magnet for interior magnet type of motor. So in this case, we have we'll select a delta shape for the magnet, which included under the layer libraries, and the name of the part is 10A. Once you select the part, it will come here and you can see a view of it, and it will come with the default set of inputs, and then you need to adjust these parameters to the shape that you want. So once you put your cursor over any parameter, it will show information what this parameter mean. It also show a graphical representation of this parameter in the view here in the middle. Once you put all the information, you can validate your part and you can see the update directly here in the middle. In our case, we don't have the skew, but if you have some skew, you can add it through this tab here. The polarization indicates the direction in which the magnet is oriented. So all the standard magnet that come with Flux Motor had a default polarization, which is typically right, and you don't need to change it. But if you want, you can use this input here to change the direction of the magnetization. The next part is to define the stator parts. So it's the same idea. There's a large set of standard library to select from, including free shape, parallel to slot, and parallel tooth. In our case, we are going with parallel to 01F part, which include the following parameters here. So we need to go ahead and define those parameters. Also, there are some hand calculation which can be done to at least find the thickness of the yoke, the width of the teeth, and so on. So it should be available beforehand, or you can just try to estimate them based on the motor dimension. And then you validate the input. You can also add the skew if you want to the stator part. Next is the winding tool. And the winding tool is actually one of the most powerful tools in Flux Motor. So here you start by defining your winding connection, either star or delta connection, and then there are different definition mode depending on what you want to do. So based on the slot port combination, Flux Motor will come with an automatic layout for the winding. But if you want more freedom, you can move to easy, advanced, and expert, where you can actually define the winding layout completely by yourself by defining the in slot and out slot for each coil. Once you define the main winding layout, you go and define the coil in the slot. So you can define the wire topology as either circular or rectangular. So in this case, we are using a hairpin winding, and so we'll go with the rectangular cross section. And then you need to define the number of turns per coil. This is typically computed based on the available voltage at the terminal for the motor, and can be done computed to target a specific back EMF. So in this case, we have 6 turns. Number of wire in hand is 1, and this is the wire dimension. You can also put the insulation thickness between the wires for the liner, for the phase separator, and so on. The next part includes the end winding of the motor, and by end winding, I basically means those two parts here. Those are important to define. They are typically not adding a lot to the electromagnetic performance of the motor, but they will add to the coil resistance and they will add to the Joule losses produced by the coil. So you can define this as U-shape or C-shape and then define the dimension you want here. The next part is the X factor is used for calibration. Let's say you have some measurement and what you are getting from Flux is not exactly matching due to some environmental effect in the measurement. Then you can come here and use this calibration factor to adjust the value. You can also target specific reference temperature, which you know the motor will be operating in, and then to see the resistance of the motor at that specific reference temperature. The next part is only important for the thermal performance. So it's actually the potting or the encapsulation of the winding. It's typically the case on this high-end motor. It prevents the coil vibration. It help insulate the coils from the stator laminated part. And it also help in extracting the heat out of the winding or the coils. So in this case, we are defining the potting, and we are giving the dimension for the potting extension. Once you define the input for the winding, you can look at the winding layout, and let me remove the input side so we can see it better. So we can see a layout of the winding here. We can see a radial view of the winding. We can see connection table, expect each coil and what is the input and output slot for it. And most importantly, we see criteria to be able to judge our winding layout. So we look at the magnetomotive analysis, which show you the force produced by the coil in the air gap. So you want this to be as sinusoidal as possible, but that's not possible due to the slotting in the stator. So we typically look at the FFT analysis of this MMF waveform and try to reduce this harmonic distribution contribution as much as possible and just leave the fundamental. Another criteria is the winding factor, which give you an idea of the utilization of the cover. So you want this winding factor to be as close as possible to 1. So in this case, it's 0.96. So that's good enough. Once we decide in the winding, now we can move to define information about the cooling. So first we go to define information about the external cooling. So the first thing is the fluid one. So in the external to the surface, in this case, we have just natural convection, and the machine is oriented in the horizontal direction. For the cooling circuit, you can define this parameter in different ways. In my case, I'm using convection coefficient inside the water jacket of 12,000, but you can define the fluid velocity and the flow also if needed. Next, you can define the radiation, which typically auto is a good one. But if you want to control it better, you can use the user mode. And again, X factor is just for calibration. For the internal part, what you need to define either to define a natural convection or a forced convection. In this case, I'm defining a forced convection here in the end winding part. So you need to define the tip speed ratio, which is the ratio between the rotor tip speed and the internal fluid velocity inside. So I just went with the default number in here. And again, you can define the radiation, but in this case, I left it as auto. And the interface mode between the different part of the motors. So you can calibrate that if you want it. So in this case, I'm just using auto in this case. So the slot connection mode is going to show you what are the model which is used to model the winding from thermal point of view. So in this case, we are just using harmonized thermal conductivity. The last part of defining the on the design part is to define the material. So in this case, we are using stainless steel for the for the housing, for the frame, the shaft, and the bearing, so it doesn't have any electromagnetic properties. For the rotor, we are using NDE FET 1050 2800. So it has a remnant flux density of 1.05 and the corrosive field is 2800 kiloamp. And for the rotor and stator magnetic circuit, we are using M33035A. And for coil, we are using copper. For insulator, we are using Nomex. And for the cooling circuit, we are using water. And the external cooling is air. So once you define this material, you can click on this one. And you can change the material if you want. So this shows you all the available material in the libraries. And you can also go to the material manager from here to define your own material for the design. Once the design part is done, you can move to the test part. So the first thing is the characterization test, and we start with the open circuit test. So there are two tests available here. The first one is the cognitive torque test, and you can actually see an overview here about what this test means and what type of result you'll be expecting from this test. So in a permanent magnet machine, the magnet has tendency to align with the slotted stator part, and this is create what's called a cooking torque. That's a torque you can feel actually even if you move the rotor freely. These torques typically need to be minimized, and because otherwise when you load the machine it can cause significant torque trouble during the operation. So you can put the information for the cognitive torque. Typically, you don't need any inputs for this test, but you can change the magnet temperature if needed. And the result you get from this test is the waveform for the cognitive torque, including the peak-to-peak information and also an FFT of the waveform of the cognitive torque. The second open circuit test is the back EMF test. This test is basically you rotate the machine with a fixed speed and you look at the voltage at the terminal of the machine. So the only input you need is the speed. Again, you can change the thermal setting in this test. And what you get out of this test typically different waveform for the phase voltage, the line-to-line voltage, and also the breakdown of the harmonic content of this waveform. You also get the flux density in the air gap and also the saturation on the stator and rotor parts. So you typically want to do this test to make sure that your back EMF is not exceeding specific limit. You want your back EMF to be 20% or 10 to 20% lower than the available voltage at the terminal of the motor, so that you can actually push current inside the motor. The next type of test is the model test, and in this test used to characterize the machine basically. So the input is the maximum line current that you can provide to the machine, which is 300, and the maximum speed that this machine can go, which is 15,000. And then there's a bunch of settings, including the thermal. So you can set the thermal in the winding bar and on the magnet. The electronics to include the losses in the power electronics, and the mechanic is to include the mechanical losses. In this case, you just define the mechanical losses at one speed, and then we have an analytical model which will scale it down for different speeds. So once you run this test, the main result is different map for the flux linkage in the DQ range. So, and those maps can actually be exported to be used as a reduced order model in other system simulation tools. The next test is the datasheet test, and this test is basically intended to find the what's called the corner point or the base point for the machine. which is defined here. It's actually the maximum speed where you can keep the maximum torque of the machine. So in this test, again, the thermal and the mechanics setting can stay the same as before, but in the electronic, there's something new. So we can define what is the available DC bus voltage. And based on your inverter control strategy, this will be scaled down, and Flux Motor will compute the maximum line-to-line voltage available to the motor. So the result you get from this test is the base speed performance, including the speed of the corner point and the mechanical torque and the efficiency. You also have information what is the optimum control angle at that operating point. You also have a lot of information, but more importantly, you have a breakdown of the losses in here. You also have information about the torque ripple that you will have in the machine, and also breakdown of the torque ripple as a percentage from the average torque. The next test is the steady state thermal test. And again, this is used to evaluate the temperature distribution inside the machine. So the main input here on the thermal setting, you can put the temperature of the external fluid and the temperature of the fluid in the cooling circuit. And you can put a set of losses here. So you need the losses in the stator, such as the joule losses and the ion losses. And you can also include the losses in the rotor part, in the rotor lamination and on the magnet, and the mechanical losses as well. So you can input this yourself, or you can import it from other tests, other electromagnetic tests that are already performed. So the main result you get is the temperature distribution on the different part of the motor. You get a radial view and axial view as well. And you can also get the main parameters defining the thermal network of the motor. The next step is the sine wave test, and this can be defined in two modes, either motor or generator mode. And you can also do, in motor mode, you can do three different ways. You can define your current control angle speed, and it can give you what is the torque and what is the efficiency, or define specific torque speed point you want, and it give you what the current and the control angle needed to reach that operating point. The next one is the square wave test. This is something specific for 6-step inverter drive, where the current has a trapezoidal waveform rather than a sine waveform, which is not the case here, but just let you know this is available if needed. The next test is the performance mapping test, and this is intended to find the torque, speed, envelope of the machine, or mainly to find the electromagnetic performance across the entire speed range of interest. So the input here stay the same as before regarding the setting, and in the input here you put the maximum line current. The maximum line-to-line voltage will be deducted from the setting you put in the electronics, and then you decide what is the maximum speed. Let's say for some reason, because the available voltage is not high enough, you cannot reach this maximum speed. You put here is actually going to give you a warning message, and it's going to tell you what is the maximum speed you can actually reach with that voltage. On the setting here, you can also include a duty cycle, and you can define it in here. So you can define it yourself, or you can actually load the file, Excel file in a specific format to fetch this information and put it here. So once you run this test, this is the result you'll be expecting. So you get information about the base speed, which you expect to be the same as the datasheet test before. But also you get information about the maximum speed, including the torque and the efficiency you can reach, and also all the losses breakdown. You can also get the different curve, including the torque, speed, envelope. You can also get different map, including the efficiency map across the all speed range. And you can also get different curve related to the specific duty cycle that's we uploaded during in the input part. Okay, so we can track how the efficiency is changing during the duty cycle. And if you go back to the tables, you can actually find this information, and you can find the average efficiency during the entire duty cycle, which is in this case is 95. So the next test is the NVH test. There are two tests you can run here. The one is just the NVH in a single working point defined by the current, the control angle, and the speed as here. The result you get here include the model analysis, which show you basically the different mode shape and their natural frequencies. You also have the Maxwell pressure in the air gap, and you have the radiating sound power, either across the different order, or you can show this against the frequency. You also get the electromagnetic forces acting on the stator teeth, which is the main source of vibration on the stator housing assembly of the motor. The second test in the NVH is the spectrogram test. And the operating points here can be defined in two different ways. So you can define the different points with the current, control angle, and speed, as shown here at the table, or you can import your own table. Or you can define, take this point directly from the torque speed envelope. So in this test, we define the setting is almost the same as the performance mapping test. So we put the maximum available current and voltage, and then we run the test. So first it will run electromagnetic test, and it will come with this torque speed envelope with different operating points in here. So those are the points where the NVH will be evaluated. And then it will evaluate the NVH and give you results such as this one, which are waterfall diagram, included the radiated sound power versus frequency and speed. So from this curve, we can already notice there are some issue around the maximum radiated sound power is around 6,000 Hertz at almost 7,500 RPM, and near the maximum RPM was of 15,000. We can also look at this graph, which show the order curve analysis, and you can look which order is contributing the most to the noise. So in this case, it happens to be order 48, which is expected for this type of topology because it has 48 slots. And then you can look at the overall radiated sound power over the speed range. And in this case, we can see that the maximum is actually happening at 7,500 and 15,000 RPM. So they give you a great insight where you could have a high noise, and you can go ahead and try to adjust your design for the motor or either the housing to try to avoid this problem later on when you go to the detailed design part.